Hello everyone, the USA Math Olympiad 2023 was just held last week, and some people have nicknamed the second day a double dose of cyanide because we do not just have one problem on combinatoric number theory, we actually have two such problems. So, without further ado, let us take a look at these interesting problems, problem 4 and 5. So problem 4 is a game played between Alice and Bob. So the problem statement is as follows. A positive integer a is selected, and some positive integers are written on the board. Alice and Bob play the following game. On Alice's turn, she must replace some integer n on the board with n plus a. And on Bob's turn, he must replace some even integer n on the board with n over 2. Alice goes first and they alternate turns. If on his turn Bob has no valid moves, then the game ends. Show that given any initial conditions where Bob can force the game to end regardless of what Alice does, the game will still end regardless of what Alice and Bob do. So you have initial configuration, Bob has a strategy to force the game to end. Then actually for that initial configuration, it doesn't even matter what Alice or what Bob does, the game will still end. So that's basically what we are supposed to show. The statement is a little bit confusing, but it is actually, once you understand the statement, it is actually quite simple to motivate the solution. So before discussing the motivation to the solution, just wanted to get a small technical point out of the way. If there's only one number written on the board, then the problem is basically done because Alice and Bob will not have any degree of freedom. They are always forced to pick that number on the board. So the statement is trivially true. Let us from now on only consider initial configurations where there are at least two numbers on the board. Okay, so how might we go about approaching this problem? So we should first try to understand the impact of Alice and Bob's move on the numbers on the board. But actually all we care about, right, is factors of 2. What do I mean? Because Bob's, what he does is he must pick some even integer and replace it by n over 2, right? And what really matters is how much further can Bob keep dividing by 2. And this is why we are led to consider this function here, which is typically called a 2-adic valuation. Or to put it simply, it describes the highest power of 2 which can divide the number. So let's say the highest power of 2 that can divide a is 2 to the power of k. And for the numbers on the board n1 to nr, let the highest power of 2 that can divide them be l1 to lr respectively. So what Bob's move does is it will lower li by 1 for the ni that he chose, right? Because he replaced that number with n over 2, so it loses a power of 2 that can divide the original number n, correct? And in fact, the game ends if Bob receives a situation where all the li's are 0. Basically, there's no even number at all. So this is why considering this highest power of 2 really matters. But what happens for Alice's move? How does Alice's move affect the powers of 2 that divides the numbers? Well, this is where we need to do a bit more analysis, but this is a critical analysis to be done. Right, so let's look at case 1 where k is bigger than l. So remember, k is the highest power of 2 that divides a, and l is the highest power of 2 that divides the chosen integer n. Right, in this case, a can be written as odd times 2 to the power of k because k is the highest power of 2 that divides a, right? And n can be written as odd number times 2 to the power of l. So by pulling out the smaller power to the power of l, you can write a plus n as 2 to the power of l times some odd number in the bracket. So the highest power of 2 that divides a plus n is still at l. Okay, so Alice's move in this case shifts the highest power of 2 from l to l. But for the other case where k is less than l, then we can go through a similar calculation. This time we pull out 2 to the power of k times an odd number. In this case, Alice's move will have dropped the highest power of 2 from l to k. And in the case k equals l, this is where we will boost up the power of 2 instead. We have a plus n equals this form, which you can pull out the common 2 to the power of k, and then odd plus odd is even. So Alice's move in this case will boost the power of 2 from k to something strictly bigger. Okay, so we see Bob's move reduces a power of 2 by 1 for one number, right? For the number that's chosen. Alice's move either maintains the power of 2, cause it to drop, or boost it to something strictly bigger. So with this in mind, it's actually quite easy to now motivate the answer. Now let's look at our powers of 2 again. So this is what we have in the initial configuration. Okay, so now we consider two possible scenarios. The first scenario is if there exists some Li with Li bigger than or equal to k in the initial configuration. So in this case, we fix that I, and I claim that Alice has a way to keep the game forever ongoing. And basically the idea is to maintain Li greater than or equal to k. Each time it drops to k, it gives it a boost to keep it strictly above k, and then if it drops back down to k, it gives it a boost again. So essentially Alice's strategy is as follows. On her turn, she just checks whether for that fixed I is Li equals to k. If so, she picks Ni to operate on. It will boost Li to strictly increase, which is what we saw in the previous slide from the case analysis. She hands it over to Bob. Comes back on her turn, she does the same check again. Because she only boosts each time Li drops down just nice to k, she will boost kick it back up, right? So it will never drop below k. Now if Li happens to stay strictly above k on her turn, then Alice wouldn't want to mess up the value of Li. She just picks any other nj, where j not equal to I, to operate on. So quite a simple strategy, and essentially Bob will always receive a configuration where Li is strictly bigger than k on his turn. So there's at least one valid move open to him, which is basically at the worst case he's able to pick Ni. So at least he's able to keep the game going in this initial configuration. Now this is the scenario where it is not covered by the hypothesis of the problem, right? Because it's not a case where Bob can force the game to end regardless of what Alice does. And what is the other scenario? The opposite scenario is basically all the Li would be less than k in the initial configuration. Here I claim that Bob can force the game to end regardless what Alice does, and in fact the game will still end regardless of what either does. Because we saw from the case analysis, if L is less than k, picking that n will cause L to stay at the value L, right? So anything Alice does will not change all Li's. On the other hand, Bob's move always decrease some Li by 1. So indeed Bob can force the game to end because he keeps decreasing the Li, but in fact, regardless of what Bob does, Alice's move will do nothing. Bob's move will decrease some Li by 1. So eventually the game will reach a state where all the Li's are zeros and the game ends, right? So that's really all there is to this question, and it's quite a simple proof, enjoyable problem to start off day 2. And so now let's take a look at problem number 5, which is another combinatorics number theory problem. And this one is really interesting. Let's try and take a look at the problem statement. Let n bigger than or equal to 3 be an integer. We say that an arrangement of the numbers 1 to n squared in the n by n table is row valid if the numbers in each row can be permuted to form an arithmetic progression. So in this case, we have a row valid configuration, because 159 is AP, 234 forms an AP, and 678 forms an AP. Okay, we say that the configuration is column valid if the numbers in each column can be permuted to form an arithmetic progression. Here we do not have a column valid arrangement, because for example 3, 8, 9 don't form AP, right? Okay, so the question is, for what values of n is it possible to transform any row valid arrangement into a column valid arrangement by permuting the numbers in each row? So if you look at this diagram, for example, this is a row valid arrangement. It is currently not column valid, but we can permute the numbers in the row to get a column valid arrangement. For example, you can permute the numbers in the rows so that 147 ends up in the same column, 258 ends up in the same column, and 369 ends up in the same column, in which case we have now obtained a a column valid arrangement. Right, so essentially to transform from row valid to column valid, you want to be able to select one number from each row so that you get an AP, and then you want to be able to do this in a way that partitions your n by n table into n APs of length n. Okay, so something that looks like this diagram over here. Now, let's talk a bit about how we might motivate the solution. So, if we think about it, the APs 159, 234, and 678 is sort of like a messy way to break up 1 to 9 into 3 APs of length 3. But our column APs that we get in the end, which is 147, 258, and 369, they are sort of quite nice ways, quite a neat way, right, of getting 3 APs out of 1 to 9, right? Basically, you keep skipping, you take the 1 mod 3 numbers, and then you take the 2 mod 3 numbers, and then the 0 mod 3 numbers. I mean, they obviously form AP, and this is quite a nice way to describe, to get our 3 APs, right? So, in a general row valid arrangement, must it be the case that 147 be in distinct rows? This will allow us to then pick 147, arrange the rows so that 147 ends up in one column. And must it be the case that 258 be in distinct rows and 369 be in distinct rows? Well, the right formulation turns out to be that either 147 must all be in the same row or all be in distinct rows. And the way to see is quite straightforward. I mean, if 1 and 4 are in the same row, there's basically no way to insert a number in between to still get your AP. So you're forced to have 147 being in the same row. Right? And similarly, if 4 and 7 are in the same row, we cannot put a number in between because 3 is not cannot be broken down into 2 equal intervals. So your only possible AP if you have 4 and 7 in the same row is to have 147 in the same row. And again, if 1 and 7 in the same row, the only possible way is to insert 4 in the middle and get 147 in the same row, right? So basically, we have shown that in any row valid arrangement, either 147 is in the same row or they are all in distinct rows. And similarly, you can prove that 258 satisfies this property and 369 follows this property as well. This means if you have any row valid arrangement for a 3 by 3 table, if 147 is in the same row, basically it occupies one row, it eliminates the possibility of 258 or 369 being in distinct rows. So all of them follow the first option of all being in the same row, in which case we can just pick 1, 2, 3, 4, 5, 6, and 7, 8, 9 as your columns in the rearranged column valid arrangement. On the other hand, if all of them are in distinct rows, then obviously you can pick 147, 258, and 369 as your respective columns in your rearranged column valid arrangement. Right, so n equals 3, we have just shown actually satisfy this property by going over these proofs of these 3 statements over here. So this should motivate, give enough motivation for what I'm going to show next. Remember, the crux of the idea is like you try and put 1 and 4 in the same row, what happens? You cannot break the interval in between them any finer, which forces 147 to end up in the same row, right? So this suggests that you may want to prove that all primes work. And the proof basically follows the same structure as our 3 by 3 example. So the central lemma is this. Let's be given a row valid arrangement. We fix k, which is the remainder after dividing by p, right? So then I claim that the natural AP, where we get all the k mod p elements, these either all lie in the same row or they all lie in distinct rows. So the proof of this is quite similar in spirit to what we have motivated earlier on. Say k plus AP and k plus BP are in the same row. call their difference CP, where C is strictly less than P, right? Because at most you have P minus 1 and 0 P. So C can be at most P minus 1. So C is less than P. Now, so for them to be in the same row in this row value arrangement, the row elements in the row form an AP, right? So these two are as part of an AP. What is the possible common difference for this AP? Well, firstly, P cannot be larger than D cannot be larger than P. To fit AP of length n within 1 to n square, the largest possible common difference is if we use 1 and n square as the extreme ends of the AP and divide it up into divide n minus 1 equal intervals in between them, in which case the common difference is n plus 1. And you can only get this common difference if and only if we use both 1 and n square. So for any other configuration, including this configuration where we clearly are not using the extremes 1 to n square, then the common difference is at most equal to n. And n here is the prime P. So we have shown that D is less than or equal to P. Now, at the same time, D cannot be strictly smaller than P because, well, the common difference must divide this difference here CP, right? So if it's strictly less than P and P is a prime, so if you think about the possible prime factorizations, the candidates for common difference are now at most C. And to cover a gap of CP with such a small D, right? Moving from this number to this number, you will need to cover the gap of CP and go through each time we can only jump a small gap, which is D. You can check that will require at least P plus 1 terms. So this means that, your row only has P terms in the AP, right? So this again shows that your D cannot be too small. In fact, it cannot be smaller than P. So this forces D equals to P, which means that the only possible AP that fits this and uses both these two numbers is our candidate elements over here. So this means all these elements in fact lie in that same row. So we have now proven the lemma. The terms mod K mod P either all lie in the same row or all lie in distinct rows. How does this prove the problem? Prove that P works. So once again, if they all lie in the same row, and this must then hold for every single K. And then we can just pick 1 to n as the column, then n plus 1 to 2n as the next column, and so on. On the other hand, if they all lie in distinct rows and this holds for every K, then we simply pick these elements, that the K mod P elements, as your columns. So this shows that we can permute the row value arrangement into a column value arrangement. But how about composite ends? So we now need to show a counter example. We need to construct a counter example where we have a row value arrangement and we cannot transform it into a column value arrangement. So say n is equals to AB, where A is smaller than or equal to B. So once again, we should try and motivate a possible way to come up with this construction. The smallest example that will fail is 4, n equals 4. And then let's see what happens if we try and argue our lemma for the series 1, 5, 9, 13. So we wanted to say 1, 5, 9, 13, they are either forced to be in distinct rows or forced to be in the same row. But the argument breaks because here, between 1 and 5, you can actually force in a number 3 and then get 1, 3, 5, 7, and that still gives you a AP, right? So in fact, you can try to put 1, 3, 5, 7 in the same row, and that breaks the lemma already because 1 and 5 in the same row, but they are not 1, 5, 9, 13 is in the same row, right? So one way to force this interweaving of gaps, right, is to basically you break 4 into 2 rows and 2 rows, and then you write 1 to 8 column wise, and then you flow 9 to 16 column wise. So this will force the interweaving of 1, 3, 5, 7 here. And once we have this configuration, you can actually check that the element 2 here is problematic in the sense that we cannot pick one number from each row so that it includes 2 and you will get an AP. I'll leave this to check yourself. It's quite easy to check. You just brute force, can I pick 1 and 2, 3 and 2, 5 and 2, and 7 and 2, and then you realize no, it cannot. So this motivates the construction we are about to prove next. So this is the formal proof of the composite case. The construction is as follows. Basically, we write n as AB, right? We break n here into B blocks of A rows each. And then we flow 1 to A, then we flow, we basically write the numbers in increasing order column-wise for each block. Then we start with the next block and do the same. So, and so on until the last block, then we get n squared over here. Okay? And we are going to show that A is a problematic element in that we cannot pick one element from each row and pick A and get an AP. So once again, the idea is analyzing whether what can the common difference D be. It cannot be too big, it cannot be too small, then we get a contradiction. So we saw previously that the common difference D cannot be too big if we want to fit the AP between 1 and n squared. In particular, we saw that D must be at most n. At the same time, D cannot be too small because intuitively it will pick up too many, the AP will cover too many terms in the first A rows, which is a contradiction. And the specific way to show this is that what can the A plus first term be, right? So if D is too small, the A plus first term, is at most first term plus A times common difference, right? And the first term, is at most A. It could be even smaller for all we know. It's at most A, then plus A times common difference. The common difference here is at most n minus 1, so it's at most AB minus 1. This evaluates to this thing, which evaluates to A squared B. So if the common difference is too small, we've shown that the first A plus 1 term must all lie inside these A rows, because A squared B is right here, right? This is A squared B here. So we show that we'll overpick terms from the first A rows, which is not allowed. There are too many terms in the first block. So this shows that the common difference is forced to be equal to n. But can we form an AP with common difference n by picking one term from each row? Well, it turns out that we cannot because the first row cannot contribute to the AP. Now, the AP terms are definitely congruent to A mod AB because A is inside, right? So this is for sure the case, which means that all the AP terms are in fact divisible by A. But the first row terms are all congruent to 1 mod A, so they are all not divisible by A. And this is where we get our contradiction. And this completes the construction, the proof of our construction. So, hope you enjoy problems 4 and 5 that I've covered from USAMO 2023. Stay tuned to the channel for more math videos and see you soon.